Greetings and welcome to Week 2, Unit 4, Basic Sciences and Engineering Sciences. Earlier, we understood the nature of role of humanities, social sciences, and management courses in engineering programs. Now we look at we try to understand the nature of basic sciences and engineering science courses. Now, one thing should be very clear at the beginning. Basic or pure sciences seek to understand natural phenomena. Its primary goal is to generate knowledge and explain why things work. So the modes will be discover, model, and predict. Whereas engineering sciences is a branch of applied sciences that uses mathematical, physical, and empirical principles to analyze, synthesize, and optimize systems, processes, and devices. So as you can see, there is a basic difference between engineering science course and a basic science course. Examples are basic science. If you take physics is a basic science course. And if you are looking for engineering sciences, linear network theory, strength of materials, these are examples of engineering science courses. Now let us look at the current practices in basic sciences. These are all the things that have come to us over a period of time, and some basic reconsideration should be done to effectively incorporate them into the curriculum. The courses in this category, as per current practices, belong to mathematics, physics, chemistry, and sometimes in biology. The number of credits for this category is presently practiced 24 or more. Mathematics, normally 2 courses are made common for all engineering branches, and 2 courses are chosen by the department. And each course is of 4 credits, so that already accounts for 16 credits. And the present practice is to use one of the several standard textbooks on engineering mathematics. These textbooks are mainly collections of several topics considered important or somewhat independently treated. That is, when you go from one section to the other, you move to a different topic altogether, not necessarily directly connected to the previous one. So each one of these courses was based on a chosen set of topics. So there is not necessarily a direct integration between the topics that are chosen. Sciences, if you take, the current practice is 1 course in physics and 1 course in chemistry. Generally they carry laboratory, so they also become 4 credits. So 4 plus 2, 6 into 4, so 24 credits. Some institutions offer a course in biology instead of chemistry. This is relatively recent practice. All basic science courses are offered as 4 credit course. In mathematics, you try to incorporate tutorial, whereas in the case of physics and chemistry, you try to incorporate 1 credit of laboratory. Any deviation from this, generally the faculty concerned with will be strongly react to that, and they don't like fundamental changes in that. Now, suggested basic science courses, now we are talking about 16. Of course, this number is considerably lower than current practice, but we will overcome that in a different way. The courses in mathematics will require a new consideration. It is not a collection of topics, but we look at mathematics that is important for engineering courses. First thing is, all engineering phenomena are dynamic in nature. dynamic in nature means the variables change with time. When something changes with time, the gradients will start becoming important. So dy by dt becomes important, and they can be modeled as differential equations. Besides, all engineers need to collect data from several sources, all kinds of sources, and process the data. So this requires a course in statistics. So I personally feel these two are compulsory courses to be given at undergraduate level. So the two courses suggested common to all branches are ordinary differential equations, linear differential equations, and statistics. These two courses are the basic ones. They can offered as four credit courses. Additional requirements of mathematics can be met through engineering science courses or embedded into corresponding professional core or professional electives. Wherever you want additional mathematical requirement, they can be embedded into either professional core or professional electives, or you can identify those courses and offer them as engineering science courses so that you are making them more in alignment with that particular branch. So if you meet the additional 8 credits requirement through this process, now we are on par with what is being practiced till now. Now let us look at, I would like to present this example, linear ordinary differential equations. If we take it as 3:1:0, the aim of the course is to enable the student to formulate real-world problems into mathematical model leading to differential equations. That means we look at real-world problems that can be modeled as differential equations. An ordinary differential equation is a mathematical equation for an unknown function of one variable that relates the value of the function itself and its derivatives of the various orders. This course is an attempt to equip the students with various techniques for solving ordinary differential equations of first degree and various orders, and make them learn to give the physical interpretation of the obtained solution. That is the purpose of broad aim of this course. Now let us look at the course outcomes. We start describing any course in terms of its course outcomes. We start with model a dynamic engineering system as an ordinary differential equation, physical description, mathematical modeling. Take examples from 3-4 branches of engineering. Problems that come, give the verbal description and say how the variables change with time, and translate them into a first order differential equation or into an ordinary differential equation. Now we solve ODEs at various levels. That goes up to CO5. Then what we do is we determine the Laplace transforms. Given a differential equation, how do I convert into Laplace transforms? That means a differential equation is being converted into some kind of a algebraic equation. And as an algebraic equation, you can solve it. And having solved it, you take the inverse Laplace transform of the given functions and solve ODEs using Laplace transforms. So this part is also very important in various branches, but that is integrated into differential equations. It is not treated as a standalone transform. Then what happens if you model dynamic engineering systems? Generally, you are not constrained to one variable, but several variables. Each variable will have its own relationship, and so you end up with a system of linear differential equations, and they and solve a given linear system of differential equations using matrices. Some knowledge of matrices should be there with 12th graduates, so we don't have to start from the basics. But additional properties that you want to present, you give that. And one feature of this is either you can treat it as a tutorial or as a laboratory if you want. Use one of these softwares that are available like Mathematica or such software to understand the behavior of the different systems. You can keep changing the parameters and see how the system behaves. That kind of physical feeling is very important to kind of internalize the significance of modeling as differential equations. Okay, statistics also can be correspondingly be presented. Now come to the other basic science course. If physics and chemistry courses are made common to all branches, the parts of knowledge provided by them are not necessarily useful to all engineering students. Students will complain, why am I learning that particular topic when I'm unlikely to use that any time in the next 3 years. So one method of addressing this issue is to make the students of these courses, contents of these courses specific to branches. That is, you call it physics, but if you want, you can name it as physics for EEE, physics for ECE, like that. Or you simply call it physics and only choose topics that are what you think are relevant to that particular branch. Some institutions offer a course on biology in place of chemistry. That is also acceptable because already many institutions are doing that. Then coming to computing areas, these days you have several branches in computing area, and these are the choices that you can have. Physics for optics and quantum mechanics, because you may be dealing with photonics and quantum computing. So corresponding optics and quantum mechanics can be offered in the physics program, or biology for bioinformatics, computational biology, neuroscience, and health technology. And this course will have topics on computational neuroscience and cognitive modeling, which will be very useful in several specializations. We'll come to see that. Chemistry for computational chemistry, materials and drug design, because these days computers are being heavily used for creating new materials and creating new drugs, significantly enhancing the productivity of this research. So you can be trained in molecular modeling, simulation of materials and reactions. That can be the chemistry course. Or otherwise, you have cognitive science. It's mainly meant for user-centered design, models of cognition. Courses like human-computer interface, AI and NLP will require this knowledge. It is at least important to that. So to that extent, if you want, you can give a cognitive science as a course to the computing branches. Now, we hope we have put these courses on par with the current practices. There is no significant difference except that we shift 8 credits from basic sciences to either professional core or engineering sciences. That's all. The suggested number of credits for engineering science courses is 14 credits. These courses can certainly be made specific to each branch. The knowledge provided in these courses should be directly relevant to professional core courses. And though they are engineering science courses, you can keep incorporating some engineering component into this. It need not be pure engineering science course. if you add a little more engineering component to that, the students will find more interesting, and they feel more motivated. So some suggested courses we'll list here: mechanical engineering, problem solving through programming, strength of materials, dynamics and kinematics, thermodynamics, fluid mechanics, heat transfer, engineering drawing, CAD and solid modeling, numerical methods. As you can see, a mechanical engineer will find interest in all of them, but obviously you can only take 14 credits from here. If you think any particular course is compulsory but is not fitting into 14 credits, you can shift it to as a professional core course. ECE and EEE, again, problem solving through programming, you can make it common. Linear electrical networks, electromagnetics, signals and systems, digital signal processing, control systems, communication systems, and electronic measurements and instrumentation. Once again, practically all courses are important here. If they don't fit into 14 credits, then some of them can be shifted to professional core. Civil engineering, problem solving through programming, strength of materials, structural analysis, fluid mechanics and hydraulics, construction materials and technology, water resources engineering, numerical methods, surveying and geomatics, and environmental engineering fundamentals. So in computing, again, you can have the first course common, or you rename it if you want. Digital logic and computer organization, data structures and algorithms, linear algebra, formal methods and discrete mathematics. Similarly, you have biomedical engineering, plenty of courses from which you can choose your engineering science courses. Aerospace and aeronautical engineering, similarly, you have many from which you can choose. Industrial systems engineering, some institutes offer this industrial engineering as a BTech program. And here also you can have operations research, manufacturing systems and production planning, human factors, ergonomics, supply chain and logistics, quality engineering and Six Sigma, systems modeling and simulation. Possibly all these courses are important for a BTech in industrial engineering. Now, basic sciences and engineering sciences should be chosen and designed in such a way that their course outcomes should become prerequisites to professional core courses. That is one of the important features of current understanding of learning. That is, if you learn something, it should be that knowledge and skill should be used as early as possible, immediately after learning that. Otherwise, we forget. You cannot take recourse to a statement saying that yes, it is important material, but you're likely to use 10 years later. That will not motivate students to learn anything. In fact, if you don't use certain knowledge, I'm sure you're all aware, knowledge for more than a year or two, slowly they start disappearing. You're familiar with the terminology, but you can't make use of that knowledge to solve any problem. So please make it as a prerequisite to professional core courses. And they should never be designed as standalone courses. That is one of the requirements. So we will try to understand the nature and structure of professional core and professional elective courses in the next unit. Thank you very much for your attention.